Okay. Hello, everyone. Welcome to one more session of What is Seminar at CMA-UBI. This CMA-UBI event. Today, we have the great pleasure to have with us Sérgio Mendes from ISCTE, Instituto Universitário de Lisboa, which is also a member of CMA-UBI. Thank you so much, Sérgio, for accepting our invitation, for being here. It's really a great pleasure. And today, Sérgio will talk us about what is the Langlands Program. So, Sérgio, please.
Okay.
Whenever you want.
Thank you very much. Thank you, everybody, for attending as well. Okay. Is it okay? The image? Yes.
Yeah.
Yeah. Okay. So I would like to thank the organizers, of course, and especially Rui Pacheco, who kindly send me this invitation. It's a pleasure to be here. Yes, I'm going to talk about the Langlands program in a very elementary way, because I think maybe that is a good thing to keep in mind, to keep these seminars in a level that even students can learn and follow. So, what is the Langlands program? This is a very good question, but I'm afraid if you ask different people, you will get different answers. I'm going to talk about the original Langlands program as it was initiated by Robert Langlands, as you see in this picture. There are other instances of the Langlands program. There is a geometric Langlands program. There is a p-adic Langlands program. There is even an application of Langlands ideas to physics, but I will concentrate on the original one. Some people call it the classic Langlands program. I like the word classic, but I'm afraid it can be a bit misleading, because classic sometimes give you the idea that most of the things are done, and this is actually the contrary. There are loads of conjectures and loads of problems in the Langlands program, the original Langlands program, that are still open. And it's actually a very good subject for young researchers to do a PhD or to start their mathematics career. Okay, so this is what I'm going to talk about. I divided my talk in 4 parts. I probably will not reach the final one, I think, because I made an essay and I'm not sure if the time is enough. But in any case, these part 4 are my own results with my collaborators. And if I don't have time to talk about it and people are still interested, and if we have a questions session at the end, we can discuss some of these results if you are interested. But let's see how it goes. So in the first part, I'm going to review class field theory, and I'm going to progress very slowly from the very basic background and pay special attention to basic examples such as quadratic reciprocity. Actually, I use quadratic reciprocity quite a lot in examples to keep things simple. And then I end with Artin's reciprocity law. Then we move to L functions. Everybody knows the Riemann-Zeta function, which is the most famous example of an L function. We will go into a very brief digression on L functions. And the idea here is to define automorphic L functions, which is one of the major achievements of Langlands. And then we will focus on the local Langlands correspondence. I thought about talking about local and global, but again, because of time, I think it's a good idea to focus on a particular case, specific case of the local Langlands correspondence. And I will show some examples, especially GL2 over a field, over a p-adic field, or any local field, actually. Okay, so class field theory. The first thing one should ask, because one of the basic ideas that people who heard already talk about the Langlands program, people know that there are different worlds. There are an arithmetic world, there are an automorphic or representation theory world, and there is an interplay, there is a relationship between these two worlds. So on this arithmetic side, it's important to know exactly what kind of fields that enters into this picture. It's not any kind of field, okay? So the fields we are talking about are global fields and local fields. The global fields can have characteristic 0. They are called number fields, and they are finite extensions of the rationals. And then you have function fields. They have characteristic P, and they are formal power series in one indeterminate. To each global field, you have attached a ring of integers, like the rational integers. And I give you a simple example. If you have a quadratic extension of the rationals, so you join the square root of a non-square number d, then there should be a d here, actually. Instead of a, this should be a d. Then the ring of integers is controlled by the residual modulo 4, okay? So they appear with two different, they have two different ways to write the bases, and it depends of the residue modulo 4. Okay, so how do we obtain the local fields I was talking about? If you have a global field, you can consider absolute values over this field, and then two absolute values are equivalent if they induce the same topology. Then you consider equivalent classes of this equivalence relation, and this is called a place. Okay, so there are two kinds of places for number fields. There are finite places, and they are in one-to-one correspondence with prime ideals of the ring of integers, and you also have infinite place. The infinite place will correspond to Archimedean absolute values, and when you complete the rationals for an infinite place, you get either the real numbers or the complex numbers. There are no infinite place for global function fields. So the infinite place, the Archimedean absolute values, only exist for number fields. So through this analytic localization for any place, you consider the completion for that place, you obtain the local fields. They can have zero characteristic, and they can be non-Archimedean, that is the p-adics or extensions of the p-adics. And then you have the Archimedean ones, the reals and the complex numbers. And in positive characteristic, you have Laurent series with coefficients over a finite field. Yeah, so more or less, this is the kind of notation we use. We consider the places. In this case, it's just prime numbers, and then you have the infinite place, and then you complete the rationals, and you obtain either the p-adics or the reals. So that there is a lot of objects that are important in the arithmetic of local fields. For instance, this is actually a characteristic of local fields and local rings. The ring of integers of a local field has a unique maximal ideal. Okay, and this ideal is principal, and so it is generated by one single element, and this element is called a uniformizer. And then if you quotient the ring of integers by the maximal ideal, you obtain a finite field, which is called the residue class field. This is only for Archimedean local fields. okay? We can try to, a bit artificially maybe, extend these ideas to Archimedean fields, and you can actually do it, but you don't get exactly the same things. For instance, the residue fields in that case, for Archimedean fields, it's not a finite field, it is the reals, okay? So, or the reals or the complex. So it is not as important as it is for non-Archimedean fields. Okay, so these arrows you see here, so on the left-hand side you have characteristic 0, on the left-hand side you have characteristic P. And the arrows mean that so either the field or the ring is contained in the next one. So Z is contained in Q, Q is contained in the p-adix or R, etc. Okay. We can assemble all these completions in one single object. This object is called the adele ring. So this was an idea of Schwalle. He was studying class field theory, and in a sense he was reinterpreting class field theory, and he came up with this idea. What he actually obtained was not the adele ring, but the group of invertible elements in the adele ring, which is called the adele group. So the idea is the following: we can perform this restricted product. So we have a system. In this case, you have the p-adix for every prime p, and then you can consider the ring of integers, okay? And you say that an adele, an element of this ring, which you can see as an infinite vector. So an element is an adele actually, so is in this A of Q, if almost all the elements are a p-adic integer, okay? And you can see that the adele ring has the rationals, because you can send the rationals through the diagonal, since the rationals are always contained in every p-adic field, and also in the infinite valuation in the reals, okay? So the rationals embed into the adele ring. Then you define a topology. It is actually the natural topology, of course. And as I said, you can consider the adele ring to be the group of invertible elements of the adele ring. And this construction also holds for global fields. It's not something that can only be done for the rationals. Okay, as a motivation for class field theory, let us discuss the problem of ramification of primes. So suppose you have a Galois extension of number fields, and suppose you have a prime ideal of the ring of integers of the smaller field. Of course, when you see it in the biggest field, this prime may not remain a prime, of course. It can split, okay? So the typical thing is there will be, say, G distant primes on prime ideals over the ring of E, the bigger field, okay? Such that the prime P decomposes. We say that it is the prime P is unramified if all these exponents are 1. If one exponent is bigger than 1, then it is called ramified. And it splits completely when there are as many prime Qs as the degree of the extension. And finally, we say that the prime is inert if it remains a prime in the extension. Of course, that can happen as well. Okay, here is a simple example. Consider the quadratic extension. This is a complex quadratic extension. So you're trying to q the square root of -5, okay? You can completely describe the ramification of the primes in this case. So suppose you have a rational prime p, okay? This is controlled by the residues mod 20. Why mod 20? Well, it has to do with the discriminant of the minimum minimum polynomial that describes the splitting field, that describes this quadratic extension. In this case, the polynomial is x squared plus 5. All right. So the discriminant is 20, and because of that, everything is controlled by the residue modulo 20. So, for instance, the prime splits completely if the prime p is 1, 3, 7, or 9 residue mod 20. It is inert, that is, it remains a prime. If it is 11, 13, 17, or 19 modulo 20, and it is a square when it is either 2 or 5, as you can see. Okay, so if you do the computation, you immediately you find that it is a square. Okay, so the Legendre symbol is well, we are going to use it later, so I can say it right now. It is a quadratic character. Okay, it is a quadratic representation, and one of the most famous formulas that appear in every elementary book in number theory is quadratic reciprocity. So quadratic reciprocity tells you something like this. If you pick a prime, say a prime p, and you consider any other prime, okay, they are connected by this beautiful simple formula. So they are not independent, actually. The primes are all related in this way. This is quadratic reciprocity. I would like to make what the reciprocity is a bit more precise, because Langlands program can be seen as a generalization of the reciprocity laws that were known since Legendre and Gauss. And so it is good to have a nice picture of what the reciprocity law means. I would like to use this simplified version of the quadratic reciprocity. So what you do is you consider this Q star, okay, and if you do that, the quadratic reciprocity law becomes simpler. It has this very simple form, which we will use later on. Okay, so let's try to make a bit more precise what the reciprocity law is. Suppose you are given a polynomial, a monic polynomial, irreducible over the integers. And then if you consider any prime, of course, you can perform reduction modulo that prime, right? But if the original polynomial is irreducible, that doesn't mean that f bar still is irreducible over the finite field, fp, okay? So here is a very simple example. So f is x squared minus x minus 1, okay? By the way, I call these polynomials, I don't know if the name is standard, but Selmer proved that for every n, xn minus x minus 1 is irreducible, okay? So I like to call this a Selmer polynomial. In this case, it is a Selmer polynomial of degree 2, but I'm not sure if this name is used. But anyway, I use it in this context. So if you hear me talk about Selmer polynomial, you know it's an irreducible polynomial of the kind xn minus x minus 1. Okay, they are all irreducibles. Okay, so in this case, we have the degree 2 Selmer polynomial, and For p equal to 5, again 5 is the discriminant of the polynomial. That's why it appears here in the residue classes. So you can see immediately that for p equal to 5, it is reducible, right? In fact, it is only irreducible when the prime is either the residue class of 2 or the residue class of 3. Okay? Because if you add 5, you get the class of 3, which is the same as -2, right? Okay, so we say that a monic polynomial splits modulo p when you consider when you perform reduction, you obtain a product of distinct factors. Okay, so splits modulo p means product of distinct factors. Okay, and then you define this set FPL of a polynomial to be the set of primes such that f splits in a product of distinct factors modulo p. So a reciprocity law actually is a rule that determines which primes belong to this set. So in the case of quadratic reciprocity, for example, you have an odd prime. Of course, you can consider 2 as well. It is a nice prime as well, a bit, although it is even, it is the oddest prime, of course. But if you consider an odd prime and you want to compute this set, so this is quadratic reciprocity, by the way, this is totally controlled by the Legendre symbol, right? Okay, so let me give you an example. If you want to compute SPL of x squared minus 29, so computing this set is the same as studying the ramification of the prime 29, right? So, well, if you try to compute this Legendre symbol 29p, you are in trouble because there are infinitely many primes. But 29 is in the residue class of 1 modulo 4, right? So by the quadratic reciprocity, you have this equality. And instead of computing infinitely many residues, you just have to compute finitely many, right? So, and you can describe completely the SPL of x squared minus 29. So here is the description of the set. Okay. So class field theory deals exactly with the kind of problems we saw before, but actually it is a bit more restricted. The problem of ramification of primes already brings something that class field theory, as it existed before Langlands, could not solve, because class field theory until Artin, it only considers abelian extensions. Okay, so if you have an extension such that the Galois group is non-abelian, then the reciprocity law is very difficult to interpret. Okay, so in a sense, class field theory is the study of the abelianization of the absolute Galois group. Okay, it deals only with abelian extensions of a given field, right? So, okay, I start with a toy example. If you have a finite field FQ, okay, you can also have a kind of class field theory for finite fields. So the main result, Artin reciprocity law, says that there exists a unique homomorphism which is close to an isomorphism from the ring of integers into the abelianization of the absolute Galois group. In this case, the abelianization coincides with the algebraic closure. So I wrote this equality here. Okay. So in general, what Artin describes in his theorem is that reciprocity law can be seen as a way that relates the arithmetic of the the multiplicative group of the field if the field is local, or the group of adele if the field is global, right? So there should be a continuous homomorphism from this CF, okay, into the Galois group of the maximal abelian extension of F. But this homomorphism is almost an isomorphism, okay? So it is not quite an isomorphism, but it is close to be an isomorphism. We will see later, using ideas of Weil, how we can modify this reciprocity in order to have a true isomorphism.
Sérgio, sorry.
Yes.
May I ask you, what do you mean by close, almost isomorphism? What do you mean by that?
Oh, yeah, okay. It's not well defined. It's not exactly an isomorphism, but it is almost an isomorphism. It's close to be an isomorphism. So the thing is, okay, what you do is, if you consider the profinite completion, then you get an isomorphism. Okay, because, well, it's not possible to be an isomorphism. Suppose you have a local field. Okay, if you have a local field, on the side you have a profinite group, which is it's the Galois group of an infinite extension. So it is a profinite group, right? Because it is profinite, it is compact, Hausdorff, totally disconnected and non-discrete. But on this side, if it's local, you have the multiplicative group of F. It is locally compact. So of course you cannot have an isomorphism. You cannot have locally compact on one side and compact on the other side. But if you complete if you consider the completion of the multiplicative group, then you get an isomorphism. Okay, so the idea is to modify the Galois group, but I will talk about that later. So we actually consider a modified version of the Galois group, which is called the Weil group, and with that modification, you get an isomorphism. Okay. What I told you is a bit different, notice, because what I told you is that we modify the left-hand side, right? We consider the completion, the profinite completion of the group of the multiplicative group of F, right? But what we actually do is we modify the Galois side. Okay. Okay, so okay, so here is a nice thought of John Tate. He wrote a very nice survey for the AMS Symposium of 1974. Let me just try to move these. Okay, so he says something like this. The ninth problem of Hilbert concerns the most general reciprocity law in an arbitrary algebraic number field. It seems to me that he underestimated its potential when he referred to it as a more special problem in number theory and devoted only a short paragraph to it. So what this means is that Hilbert thought that a non-abelian reciprocity law was, a kind of a problem in algebraic number theory, a simple problem that should be fixed in a few years. But it was not like that, because these ideas of Hilbert, when he wrote these problems for the Congress in Paris, this is in the beginning of the 20th century, right? And Langlands' ideas, which give a very satisfactory answer for the non-abelian reciprocity law, only appears in the 70s of last century, so 70 years later. So it was not just a simple matter of time. Well, it was a matter of time, of course, but a lot of new ideas was needed. That is the point. Okay, so let me briefly survey L functions. Okay, so the most famous L function is the Riemann zeta function, and L functions in general, so they are similar to the Riemann zeta function in the following sense, that they usually have some arithmetic information attached to it, okay? And we would like them to behave more or less like the Riemann zeta function. What do I mean by behave like the Riemann zeta function? I mean that if you have a proposal for an L function, you would expect that it would have a Dirichlet series expansion, just like the Riemann zeta function. It would have an Euler product. It will satisfy some functional equation, and even it will probably conjecturally satisfy some kind of Riemann hypothesis about the distribution of primes. Okay, in some sense. One of the first L functions that appeared is the Dirichlet L function, which you can associate to every Dirichlet character. Okay. Of course, if you consider the trivial character, then you recover the Riemann zeta function again. Okay. Okay. So another example is the Dedekind zeta function. In this case, you are in a similar situation, but you have a number field, not necessarily the rationals. Okay. So what you do is, for the Dirichlet series expansion, for instance, you consider a summation over all non-zero ideals of the ring of integers, and then you have a norm map for each of these ideal. So this gives you a number, and so this is the Dirichlet expansion for the Dedekind zeta function. Then you also have the Dirichlet series expansion, and so on and so on. And of course, if your number field is the rationals, again you recover the Riemann zeta function. Okay, so one of the most interesting L functions is actually the Artin L functions. Okay, so how do we define this Artin L function? First, we need to define what an Artin representation is, because Artin L functions are attached to Artin representations. So you consider a finite Galois extension of the rationals, call it E, right? And you consider the finite Galois group, and then you consider a representation of the finite Galois group. This is actually a special case. These Artin representations are a special case of Galois representations, which are representations of the absolute Galois group. Okay, and then you have to consider a prime, which will be unramified in the extension E. Okay, and for each such prime, you can associate a Frobenius element, a special element in the Galois group. Okay, and with that you can compute a certain polynomial, right? And function as an Euler product. Okay, so it is directly an Euler product. Of course, in this case, you don't have a direct way to represent the Dirichlet expansion, but you have an Euler product, and that is enough. You can if you compute a few elements, you can find the first elements in the Dirichlet expansion, of course. Okay, so let's just recall again, because I'm going to use it in the next example. Let's recall again the quadratic reciprocity in its simplest form, reduced form, okay, as we saw before. And so here is a simple example of an Artin representation. So the left-hand side of the quadratic representation, so the left-hand side, right, is actually a one-dimensional Artin representation, right? Because for every unramified prime, we can associate the Frobenius to be the identity when it splits in the extension, or the non-trivial element when it is inert, when it remains a prime. Okay? And so we can associate an Artin L function. And of course, since we are doing the product over all the primes, we need to know the formula for the even prime and for Q. So these are the formulas in the bottom, okay? So this is maybe not maybe, it is certainly the most simple Artin function. Okay, here is a not so simple example. In this case, we have the Selmer polynomial of degree 3, which we know already it's irreducible, okay? And then the discriminant is minus 23, right? And so it's easy to write the splitting field. You have to adjoin to the rationals the square root of minus 23 and alpha, where alpha is a root of the Selmer polynomial, okay? So the Galois group in this case is the symmetric group, okay, S3. It is non-abelian, okay? So because it is non-abelian, we cannot expect that class field theory completely tells us how to describe the splitting of primes in this case. It is quite complicated, right? Even for a simple extension as this, it's an extension of degree 6, right? So it seems not to be a big deal, but the fact it is not abelian is already a big deal. Okay, so the idea is how to compute an Artin function for this case. So what you do is you have a two-dimensional representation of the symmetric group S3, right? Call it phi. It's described here, okay? And then what you have to do to compute the function is you have to decide the class for each prime, 2, 3, 5, etc. You have to decide the class of the Frobenius, and you have to compute the polynomial. Well, to compute the polynomial it's not difficult, of course. So maybe the more difficult part is to compute the classes. So in this case, we are in S3. The classes can be 1 cycles, 2 cycles, or 3 cycles, right? So 3 cycles, 1, 2, 3, okay. Of course, you have also 1, 3, 2, but they are in the same class, of course. 2 cycle, 1, 2, and 1 cycle, for example, the class of 1, right? Okay, I did some computations. Let me check here. Okay, so how do we compute this? How do we infer what is the class at each prime? So what you have to do is you need to know if minus 23 is a square modulo the prime, and you have also to know if minus 23 is a root of the Selmer polynomial modulo the prime. So I made the computation, well, I made all the computation, but for instance, just to give you an example, for the prime 2, of course, minus 23 is a square, of course, because you have the square root of minus 23 square, right? So it is a square. And it is not a root of the Selmer polynomial. Why? Because you have minus 23 to the power of 3, so it is odd. Minus 23 is again odd. So odd and odd is even. Minus 1 is odd, right? So it is not 0. For instance, for the prime 59, which doesn't appear here, okay? I don't have the factor because it was too long. So for the prime 59, 59, the polynomial, the Selmer polynomial actually reduces and has 3 different roots, okay? Decomposes as the product of x plus the class of 55 times x plus the class of 46 times x plus the class of 17, you see? And minus 23 is also a square modulo 59, because if you add minus 23 with 59, you get 36, which is a square, right? So in this case, it belongs to the class with 1 cycle, and then you get the polynomial. So, and from the polynomial here, you can guess how the factor of the function is. So it will be something like 1 divided by, so 1 minus 2 times 59 to the power of minus s plus 59 to the power of minus 2s. So you can read off the factors of the function from the polynomials, see? So it's not completely difficult to compute this Artin functions. Okay, so Artin's conjecture is actually a conjecture that is related with the properties we would like L functions in general to have. Okay, so for instance, Artin conjectured that if you have a finite Galois extension and you have call it sigma, such that it is irreducible with dimension bigger than 1, then the Artin L function should be an entire function. This conjecture is still open in full generality. Okay, so it is not completely solved yet. Okay, I think I have a few slides here, a little bit technical. So I will try to explain you the ideas without going into too many details. The idea is, if you have a number field, you consider a place of that number field, right? And then if you consider the general linear group of this global field, for each place, you have also the general linear group of a local field. And you can also have the general linear group over the ring of integers. This last one is a maximal compact subgroup of the former, right? And so you can consider the system over all places of GLN FV and GLN OV, okay? And you consider this system, and you can compute a reduced product, just like, well, more or less as we did in the adeles, okay? So it is a similar construction, and you can define an adele group. So this G of A is actually a kind of general linear group over the adeles, right? And then if you denote Z G of A, the diagonal of this this group, sorry, the center of this group, okay? Then you consider the Hilbert space of left cosets, okay, of square integrable functions which verify a certain cuspidal condition. This 0 here means the cuspidal condition. So actually this condition is that some integral must vanish, okay? And this is quite typical in representation theory. When you have a representation of a group in a Hilbert space, you can define a right regular representation, okay? And then you consider any representation over this adele group, okay? And you can see it as a restrict product. What restrict product means here is that almost all these representations P of V are unramified. Unramified means that, this will be clear in the third part, they have a GLOV fixed vector, okay? They are all irreducible over the group GLFV. Okay, so the idea is to define this automorphic representation. We say that the representation appears in the right regular representation if it is isomorphic to a sub-representation, right? And then an automorphic representation is a unital, irreducible representation of this adelic group, such that it appears in the right regular representation. So it is a sub-representation of the right regular representation. These are the automorphic representations. Okay, so now if you consider finite set f of pi for an automorphic representation pi, okay, such that it is unramified outside this set S of pi, okay, you consider that, and what happens is that these unramified representations, they can be, they are, actually there is an injection to a torus. A torus here you can see as n copies of the multiplicative group of C, okay? So in a sense, to each unramified representation, you associate n complex numbers, okay? And then, of course, the symmetric group acts on this torus, and you can consider equivalence classes, okay? And this conjugation class actually completely determines the representation pi of V, okay? And because it completely determines this representation, so f pi V or f AV is exactly the same thing, okay? This was what led Langlands to define the automorphical function. So to the representation pi, he considered local factors, and each pi of V is given by a determinant which is involved with this diagonal matrices I told you before. Okay? So this is the way he defined automorphical functions, and this was maybe one of the biggest achievements of his theory. With Jacquet and Langlands in I think 1970, I think they published a result which says that these automorphical functions have very nice properties. They extend to entire functions, okay, and they satisfy a functional equation, just like we expect L functions to behave, right? I don't have time to explain these epsilon factors, but they are just a factor that appears. For us, it's enough to appear in the functional equation. And finally, we can state Langlands reciprocity conjecture. Okay, so Langlands conjectures that if you have a finite Galois extension, okay, and you have an irreducible Galois representation, then there is an automorphic representation associated with this Galois representation, such that the two Galois functions coincide. Okay, so this is the L function version of a reciprocity law. Okay, so in its L function form, a reciprocity law is an equality of L functions that are attached to different objects. On one side, you have an arithmetic object, sigma, a representation of the Galois group. On the other side, you have an analytic object. You have an automorphic representation. It's a representation on an Hilbert space. So a reciprocity is this equality of two different nature objects, you see. Langlands reciprocity implies the Artin's conjecture. Of course, it is not proved in full generality. Otherwise, we would have for free the Artin conjecture. Okay. But it is proved in some examples. Okay, just to give you an example, let's go back again to the quadratic reciprocity. We saw that on the left-hand side, if you remember, on the left-hand side, we could see the left-hand side as an Artin representation. Now we look into the right-hand side of the quadratic reciprocity, and in this case, you can interpret it as a quadratic character, which of course is a special case of an automorphic representation. It's a very basic automorphic representation. It's a character. So a one-dimensional representation. But in any case, the quadratic reciprocity, so that the equality we have here, tells you that you have an equality of two L functions, right? On the left-hand side, you have an L function that is associated with the left-hand side of quadratic reciprocity, and on the right-hand side, you have the right-hand side of quadratic reciprocity. So again, the Langlands reciprocity in its very, very most basic example is quadratic reciprocity, you see. Let me see how much time I have. Maybe I should be able to finish. No?
Like 5 minutes, it is okay for you, Sérgio?
Yes.
More?
Yeah, no, it's okay. Actually, I use these results here as a kind of safe exit door. If I don't have time for the last part, we will end with a very nice result of Langlands, which is Langlands reciprocity. Okay, but let me just tell you more, just a little bit, to enter into the local Langlands correspondence. So in 5 minutes, okay. All right.
Okay.
Thank you. So now what we try to do is is to modify Artin homomorphism. So we actually we will not change the arithmetic side. We will not change the multiplicative group. We will change the Galois group, right? So this was an idea of Weil because there were L functions called ISCTE L functions, which were also people know this for a long time, were also Artin L functions. So there was an overlapping of the theory. See, at one sense they could be seen as a kind of L function called ISCTE L function. On the other sense, they are also Artin L functions. So Weil tried to create an environment, a group, right, where this overlapping would be unified in a single theory, okay? And he came up with this idea of the Weil group. So the idea is the following. Okay, I will skip the Archimedean part because it's very easy. So let's explain the non-Archimedean part. So consider a non-Archimedean field, okay, with residue field K. And then you have the Frobenius, which is an element of the absolute Galois group of the residue field, okay? And you consider the group generated by powers of this Frobenius element, right? And of course, these groups are not the same because this group is discrete and this group is profinite again. Even for finite fields, the absolute Galois group is a profinite group, okay? So these groups cannot be the same. So, and then if you have the absolute Galois group of the bigger field of F, right? You have the canonical surjection into the Galois group of the absolute Galois group of the residue field, right? And you call phi that surjection, and then you consider the fiber of the Frobenius element. That is by definition the Weil group. So what is the Weil group? This is a bit abstract maybe, but I think this Schottische sequence tells you a better idea. So in a sense, the topology is completely modified, you see? So you have the Weil group is dense in the absolute Galois group, yes, but it has a different topology. It has the initial subgroup, which is the kernel of the map we saw before, as a subgroup, but as a subgroup, it has the profinite topology. On the other hand, if you quotient the Weil group by the kernel of phi, by this inertia subgroup, you get Z, the integers, right, with the discrete topology. So in some sense, this Weil group is a locally profinite group. It's not a profinite group, it's not compact, it's locally compact. So it is very similar to the absolute Galois group, but for the representation theoretic point of view, it has more representations, okay? Compact groups don't have many representations. For instance, every representation is finite, okay? Locally compact groups have much more representations. So this is more or less the philosophy. And now Artin's reciprocity becomes, in terms of Weil groups, becomes an isomorphism. Of course, you have to consider the abelianization of the Weil group. By the way, abelianization of any group, if the group is topological, we are talking about topological groups. If the group is topological, is the quotient of the group by the closure of its commutator. Okay, so it becomes an abelian group. So because F, the multiplicative group of F is abelian, of course you cannot have on this side the Weil group. You have to abelianize the Weil group. And the idea of Langlands is quite simple actually. For each quasi-character, a quasi-character is just a complex continuous it's a continuous homomorphism into the complex numbers, okay, the multiplicative complex numbers. So for each quasi-character of F cross, if you compose with the isomorphism of class field theory and the canonical surjection, okay, you get a quasi-character of the group, the Weil group, right? And so his idea is as simple as this. So F, the multiplicative group of F is GL1F, okay? So if you dualize if you dualize Artin reciprocity, what you get is quasi-characters of GL1 of F correspond to one-dimensional representations or quasi-characters of the veil group. So maybe if you have any representation of GLN F, notice that this is quite analytic. This is not finite dimensional, right? So it's these representations are infinite in general. Okay, they are representations in Hilbert spaces. So maybe you can correspond representations on this side, this analytical side, to represent n-dimensional representations of the veil group. So this was Langlands' idea, which he wrote to a letter to André Weil, and this was the very beginning of the Langlands program. Okay, so I don't have time to explain it completely, but in a sense, this local Langlands correspondence associates representations, class of representations of any reductive group. Just think about GLN with certain representations of the veil group. It's not exactly the veil group, it's the veiled Ling group, because then you have issues about the topology. But you can think of the veil group it's good enough. And well, this map usually has fibers, so you get the partition of the left-hand side, except when G is GLN. In that case, it is a bijection. Okay. So I think I will stop here, and just to show you some results about connected with the results on the Langlands program. Okay, thank you very much.
Okay, Sérgio, thank you so much for this lovely talk. I don't know if someone in the audience has some questions or some comments. If so, please, you can unmute or just chat your questions. May I ask some naive questions, Sérgio?
Oh.
I think in the Langlands program as a kind of dictionary between different mathematical ideas. This can be interpreted here as this reciprocity principle?
Of course, yes. For example, the correspondence I showed to you, right? So on one side you have what we call L parameters. We have representations of that veiled Ling group. On the other side, you have completely different objects. You have, okay, maybe I can show you an example. Okay, is that okay? I think it explains quite well the point I want to make. Yes, so suppose, for example, this situation here, this first situation, right? So on the left-hand side, so here is you have precisely the correspondence for GL2 of F, okay? Representations of GL2 are of three kinds, okay? So they are the principal series, which is the first case. They are the supercuspidal, okay? And they are reducible principal series in a sense, okay? So they correspond to one and precisely one object on the other side. So for instance, if you have the principal series, what you have is you induce from a Borel subgroup. This is just the subgroup of upper triangular matrices, 2 by 2 matrices, right? And you consider two characters of the ground field of F, okay? And then you induce and you obtain a representation which is called representation of the principal series. And what you do to match on the other side is, so to the other side, it should correspond something. And this something is, you have characters of the veil group now, but characters of the veil group, so this is the dictionary you are talking about, characters of the veil group, because of class field theory, can be seen as characters of the multiplicative group of F. Okay, of course, this is the most basic example, right? But so in general, you get that dictionary, as you said. But this is much more than this, because you know, the correspondence is not a completely naive one. You actually ask a lot of things. For example, you have L functions on both sides. You have Artin L functions and automorphic L functions, and you want these L functions to match each other. They should correspond. You see, so this forces the correspondence to be quite natural in a sense. But of course, the dictionary you were talking about is much more than that. You could not expect that anytime you have say a concept on one side, it corresponds exactly to the same concept on the other side. Let me give you an example. There is one interesting concept, which is the depth of a representation. So you have the depth of a representation. This was defined many years ago by Moy and Prasad. And you also have an idea of depth of a Galois representation. Okay, so in a sense, the non-Archimedean fields, because there is a lot of filtration in the arithmetic of these fields. So if you have the multiplicative group, there is a bunch of subgroups, and you can consider a filtration, an infinite filtration of this group. And you also have that for the additive group, and so on and so on. And because of these filtrations, in some sense, when you deal with non-Archimedean fields, at some point they behave like finite objects, because the representations become trivial after a certain point in the filtration. You know what I mean? So this is what depth means. Okay, so you have a representation, and how deep you need to go into the filtration so that you get something meaningful, because at some point it will become trivial, right? So there was two concepts of depth on one side and on the other side. Of course, they do not completely coincide, but they can be related in both sides. So the Langlands correspondence permits that. Also, if anything happens, so this is called the principle of functoriality. If anything happened on one side, you should expect something would happen on the other side as well, okay, and vice versa.
Thank you.
Thank you.
I don't know if anyone has something to add, something to ask or to comment. Well, if not, I would like to thank Sérgio again for being with us today and for this nice talk. I'm clapping by everyone, I think. And okay, I will stop recording right now.